Good evening. In this presentation, we would like to talk about the contortions or folds that we have recognised and defined in the Tasmanian Wilderness World Heritage Area, shown in purple on the map on the left, their significance and their implications. The folds occur at different scales, from the outcrop to the hand specimen scale to regional scale fold naps and isoclinal fold pairs with axial surface trace lengths of tens of kilometres up to 200 kilometres. Many of the folds have curved hinge lines typical of development in simple shear. Why are these folds present and what do they tell us? They clearly are a product of crustal deformation and an apparent shortening in the rock layers. The amazing scenery and landforms of the Tasmanian Wilderness World Heritage Area. The Tasmanian Wilderness World Heritage Area is one of the largest conservation areas in Australia, approximately 25% of Tasmania. It has a length extent of about 200 kilometres and a width extent of about 70 kilometres. It's one of the last expanses of temperate wilderness in the world and contains extensive areas of recent glaciation. But the rugged and in part densely vegetated World Heritage Area also contains one of the best examples of, and perhaps the largest aerially exposed region of a deformed continental margin beneath an abducted ophiolite. Uplift and erosion of the ophiolite sheet has provided an extensive window into the structures and structural regime of the deformed and metamorphosed rocks below the ophiolite. In the accepted Berrien-Crawford arc-continent collisional model involving margin subduction, exhumation, and ophiolite abduction, the leading edge of the then Tasmanian microcontinent entered an east-dipping subduction zone around 520 to 515 million years ago. The edge was abducted to depths of 70 or 80 kilometres, undergoing high-pressure metamorphism. After slab drop-off of the dense mafic and ultramafic keel or toe, the margin underwent rebound and resultant exhumation, with emplacement beneath the advancing oceanic lithosphere of the Proto-Pacific Ocean. The result is a stacking of sheets of different metamorphic grade beneath a slab of oceanic lithosphere, i.e. the abducted ophiolite. But this ophiolite has largely been removed during significant late Cambrian early Ordovician uplift and erosion as part of the rebound, plus further Middle Devonian uplift and erosion. The Tasmanian Wilderness World Heritage Area is largely coincident with the Tyennan Domain. The Tyennan Domain consists of a north-south trending elongated belt of Mesoproterozoic to Neoproterozoic rocks occupying central Tasmania. They make up 80% of the Tasmanian World Heritage Area. What is the Tyennan Domain? It is the apparent geological core of Tasmania. Originally defined as the Tyennan nucleus or geanticline, it is now considered as an allochthon or allochthonous slice and represents the internal zone of Berry 2014. It contains some of the oldest rocks in Tasmania, some of the most complexly deformed rocks, associated with high-pressure metamorphic rocks with pressures up to 1.96 gigapascals, indicating metamorphism to depths of approximately 70 kilometres. The allochthon consists of structurally intercalated slices of low and high-grade metamorphic sequences. The Tyennan Domain is a composite stack of allochthonous sheets with a maximum deformed thickness of approximately 10 kilometres based on thickness determinations in the southern part, that is, the southern Tyennan subdomain. The stacking order includes high-grade pelite, the orange-brown unit, overlying low-grade pelite, the pale orange unit, and low-grade quartzite, the grey unit with a basal platy quartzite. Below the quartzite sits the parautochthon, shown by the khaki unit. This is the lowest structural unit in the crustal stack. Overlying the allochthon is the ophiolite sheet, consisting of the ultramafic, shown in green, and oceanic melange, shown in pink, and the low-grade sheet or part parautochthon, shown in light blue. This map of Western Tasmania highlights the major tectonic and crustal components that were created or modified in the Cambrian arc continent collisional event. The allochthon label 1, that is the remaining intact part of the Tasmanian microcontinent, extends from northwest Tasmania to King Island. The interface with the allochthonous units to the east is along the Arthur high strain zone or Arthur structural metamorphic zone, circled element 6. The small relics of the ophiolite and oceanic melange, bright green, circled element 2, is the upper part of the upper allochthon. Low-grade allochthonous to parautochthonous units beneath the ophiolite, the unit formation, are shown by the light blue units, circled element 3. The major allochthon is the Tyennan Domain, shown in shades of orange, as circled element 4. This is the focus of the talk. The Dundas Fossey Graben, hosting the Mount Reid volcanic system, is shown in pale yellow, as circled element 8. This rebound-related crustal extension caused separation of the north coast fourth block Proterozoic rocks, or Tyennan equivalents, from the Tyennan allochthon. To develop the Tyennan Domain macrostructure and crustal architecture, we utilised a modified European Alps approach. The Alpine geologists constructed superb sketch profiles and cross-sections based on observed relationships in the Alpine mountainsides. But the European Alps has exceptional relief and exposure in serial ridge sections. In southwest Tasmania, we do not have the same relief, and there is significant vegetation cover in places. So, distant views of the ranges and ridge lines provided the answer. Photographs by bushwalkers, including Grant Dixon, David Noble, and Becca Lunnan, enable serial profile construction along the various ranges. The other issue was the complexity at the outcrop scale and having detailed scale-dependent observations. Seeing the large-scale structure becomes problematical. It is like the analogy of the ant on the elephant. What can the tiny ant make of or understand the gross form of the elephant? As a consequence, the bigger structural picture of the Tyennan had remained elusive. Development of the macrostructure clearly has to be an iterative approach, zooming in and out, utilising the outcrop scale detail, combined with TAS list map layers, including the MRT digital atlas maps and Google Earth imagery, along with the distant views captured in the bushwalker photographs. It is also important to realise that to develop the current Tyennan macrostructure and crustal architecture, we had to approach the problem like a jigsaw puzzle. Firstly, we had to create the pieces before we could complete the puzzle. So stage one involved construction of the jigsaw pieces, where we had to identify and geometrically define the individual macrostructural elements. Stage 2 involved fitting the jigsaw pieces together. We had to put the elements together into maps and regional profiles to complete the overall Tyennan Domain structural picture. Stage 3 involved the interpretation and establishing the structural significance of the Tyennan macrostructure. It has been a long process, 8 years, to complete the detail of the central and southern regions. We have just finished the eastern Tyennan area around Strathgordon and are currently working on the northern part of the Tyennan around Cradle Mountain. The results and ideas to date are published in our 2024 Australian Journal of Earth Sciences, Volume 71 review paper. 2 examples will be presented to illustrate the approach used to develop the Tyennan allochthon structure and relationships in macrostructure. These include the Frenchman's Cap area and the Western Arthur Range and Federation Peak. These are iconic parts of the Tasmanian Wilderness World Heritage Area. The details of the work undertaken in both these areas can be accessed in the Mineral Resources Tasmania publications as Geological Survey Papers 6 and 8. A series of Geological Survey publications 6 through 13 provide the details of the work undertaken as well as the basis of the interpretations. Now to the spectacular glacier-sculptured quartzite peak of Frenchman's Cap. The aerial helicopter view is looking to the southeast along the Lake Gwendolyn Cirque Valley. This aerial view shows the quartzite ridgeline from Clytemnestra to Frenchman's Cap with the quartzite in fault contact with the underlying dolomitic phyllite of the parautochthon. It also shows the region is essentially a tectonic stack of 3 different lithological units, including garnet schist on the top, on the west, overlying quartzite, the central part, overlying dolomitic phyllite on the right. This tectonic stack is now shown in map view with the quartzite of the ridgelines, including Clytemnestra, Frenchman's Cap, and Agamemnon shown in blue, with the underlying dolomitic phyllite of the Scotch fire metamorphic sheet occupying the lower areas shown in khaki. The higher structural sheet of high-grade garnet schist structurally overlies the quartzite, as shown in the northwest corner of the map. The green line through Frenchman's Cap shows the position of the structural profile in the next slide. This structural profile through Clytemnestra and Frenchman's Cap provides one of the best exposures of the basal quartzite of the Franklin sheet overlying the dolomitic phyllite of the Scotch fire metamorphic sheet, considered the parautochthon. The contact is a fault reactivated basal high strain zone characterized by an intense transposition foliation incorporating rootless mesoscopic isoclinal folds and overprinting crenulation cleavages. The quartzite of Frenchman's Cap shows marked structural zonation within the hinge of a major west-closing recumbent isoclinal fold, best seen in the ridgeline to Mount Moore shown on the top left. The folds within Frenchman's Cap itself are shown in the image on top right. The northeast face of Frenchman's Cap provides a superbly exposed profile from the top of Frenchman's Cap at 1,446 metres to the lake level of Lake Tarhoon at 960 metres. It shows the marked structural zonation in the quartzite of an upper folded zone with large-scale recumbent isoclinal folds, overlying a basal intensely foliated zone with mesoscale isoclines and rootless folds. The upper part of the underlying dolomitic phyllite is also intensely foliated, giving an approximately 300 metre total thickness of intense foliation across the quartzite-dolomitic phyllite interface. Now to the Frenchman's Cap fold structures. The stitched photograph is of the west wall of the late Gwendolen cirque. It shows an extremely oblique intersection with the west closing isoclinal recumbent macrofold exposed through Mount Moore. The fold has been named the Frenchman's Cap recumbent fold. At the south end of the Agamemnon ridge, there is a spectacular east closing recumbent fold hinge. This has been named the Agamemnon recumbent fold. So we have identified two major oppositely closing folds within the Frenchman Cap and Agamemnon ridgelines. The folds appear to sit at the same structural level above the basal high strain zone in the quartzite. These structural relationships are shown in the inset sketch diagrams on the lower left and upper right. Convergence of the quartzite ridges towards the Franklin River to the north, combined with the oppositely closing form and the relationship of the fold hinge lines to the stretching lineation, shown by the green green line trace, all suggest the presence of a major sheath fold at the base of the quartzite sheet. Our interpretation is shown here. Note the interpreted sheath fold has an approximate 5 kilometre width and sits at the base of the Franklin sheet on the lower limb of the regional scale Franklin fold map. The structural profile is from the central Tyennan subdomain. It shows the folding effects of younger Devonian deformation as broad, open to close anticlines and synclines. Now to the Arthur Ranges. The Arthur Ranges provided the first evidence for regional development of asymmetric macro-fold pairs. Occupying a large area, these folds have been interpreted as asymmetric fold wave trains. This aerial helicopter view at the northern end of the Western Arthur Range shows the range is dominated or held up by the Western Arthur anticline, a younger broad open anticline. The anticlinal hinge coincides with the topographic high of the range, and the range flanks, defined by dip slopes in this foliation, are the limbs of the anticline. The anticline folds a south virgin asymmetric fold couple across the range. The north closing recumbent fold occupies the main ridgeline, whereas the south closing hinge lies along the northern range flank. The fold pair is faulted at many points along the range. Some of the fold profiles are shown in these Peter Dombrovskis photographs of Mount Hayes, both looking to the northwest, and of the southeast face of Mount Hesperus. The Mount Hayes profile shows a north-closing macrofold hinge thrust over a south-closing macrofold hinge. The Mount Hesperus face shows an upper limb transition into the hinge of the major north-closing recumbent fold that dominates the Western Arthur Range. This is a David Noble photograph taken from Mount Sirius at 1,151 metres. It provides a view along the Western Arthur Range above Lake Oberon. It shows the dominant north-closing recumbent fold in the peak on the right side of Lake Oberon, as well as in the face of Mount Capricorn in the next ridge segment. The stitch photo shown here is a view of the Western Arthur Range between Lake Saturn and Mount Canopus, looking towards the eastern end of the range. As seen in the serial profiles through the ridgeline, the north closing recumbent fold hinge occupies the spine of the range. Now to the iconic jagged tooth-like Federation Peak at 1,225 metres, showing the ice-sculptured northwest face with a sheer drop into the lakes Gaston and Payens at approximately 640 metres elevation. Hidden within the quartzite ridge is the north closing recumbent fold hinge cut by a series of steeply dipping high-angle reverse faults. The pink lines are form lines within compositional layering. They depict or highlight the north closing macro-fold hinge. The macrofold is plunging towards the camera at approximately 25 degrees into the Cirque Valley. This macrofold hinge is continuous through the alternating bands of quartzite, pelite, and interlated pelite quartzite that make up the Federation Peak Jeeves Bluff ridgeline. These examples from Frenchman's Cap, the Western Arthur Range, and from Federation Peak illustrate the nature and scale of the folds that occur within the Tyennan Domain. Now, from the examples to the interpreted Tyennan crustal structure. The following slides provide a synthesis and a summary of the regional Tyennan structural relationships and macrostructure. The Tyennan crustal structure is made up of 5 sheets. We consider the Tyennan allochthon is composite made up of 2 sheets, the yellow sheet 3 and the pink sheet, sheet 4. This interpretation is based on differences or changes in sedimentary younging, the order of sheet stacking, the transport direction, and asymmetric fold vergence. The dominant or largest sheet, the Franklin sheet in yellow, has upward younging, the high-grade metamorphic rocks at the top, and a west over east transport sense. The pink sheet, Davy sheet, structurally underlies the Franklin sheet. It is upside down, downward younging, has an inverted unit stacking with high-grade rocks at the base, and a general east over west transport sense. The allochthon is made up of crustal scale slabs with strike lengths up to 150 kilometres, i.e. the yellow sheet, with dip length scales of about 50 kilometres and structural thicknesses of 5 to 10 kilometres for both the yellow and pink sheets. The structural character of the Tyennan is represented by isoclinal folds commonly approaching recumbent form. Folds with curved hinge lines, typical of sheath folds, transposition layering and overprinting crenulation cleavages, a pronounced and consistent mineral stretching lineation, and 4 major structural elements or components bounded by high strain zones. These are all part of the stacked composite sheet. The map shows the regional scale structural elements that we have identified. These are the pieces of the jigsaw puzzle. They include the leading edge fold map, shown by the red envelope on the left, the mega sheath folds, shown by the green envelope in the lower middle, the isoclinal fold stack, shown by the blue envelope bottom left, and the asymmetric macro fold wave trains map right, shown by the blue envelope as Z or East Virgin asymmetric folds, and the red envelope as S or West Virgin asymmetric folds. In summary, these 3 maps show the breakdown of the Tyennan allochthon through the various components. Firstly, the lithotectonic units, secondly, the structural sheets, and thirdly, the macrostructural elements. Now we will look individually at the major macrostructural elements. Firstly, the leading edge isoclinal fold map. This extends from Nye Bay on the coast to Cradle Mountain in the north with a strike length of some 210 kilometres. The fold has an inclined plunging to recline geometry. High-grade schist occupies the core of the fold. Secondly, sheath folds. Sheath folds have curved hinge lines and ovoid cross-sections. See D on the lower left. They are commonly bisected by the mineral stretching lineation. See A on the upper left. And often show multiple lobes or sheath-like protrusions. See the two protrusions on the lower right. They occur at all scales. Sheath folds are a product of general shear and simple shear. The folds over time, from Tn to Tn plus 1 in the diagram, evolve into tongue-like sheath protrusions with the early formed fold hinge lines, initially orthogonal to the shearing direction, rotating towards the overall stretching direction in a general or simple shear deformation. Two large-scale or mega sheath folds with 20 to 25 kilometres length scales occur or have been identified within the structurally lowest Davy sheet. These are the east closing to Witt Propstein megasheath and the west closing Southwest Cape megasheath. They are slightly offset east and west closing megasheath fold pair. See the schematic sketch on the bottom right. Note the sheath interpretation is supported by the stretching lineation trend shown by the blue arrow. The last major component presented is the asymmetric fold pair wave train that have an appearance in profile of a set of breaking ocean waves. The fold pair is generally preserved within quartzite of the various ridge lines. In profile, the asymmetric folds appear within augen-like features that have tube-like form along the length of the many ranges. The example on the right is along the Prince of Wales range. The next stage involved fitting the structural elements, i.e. the jigsaw pieces, together to create structural profiles. 3 structural profiles were created. One for the southern Tyennan, the southern part of the Tyennan Domain, one for the southern eastern Tyennan, the middle part of the Tyennan Domain, and one for the central eastern Tyennan Domain towards the northern part. Their locations are shown by the blue lines on the map. Each profile groups the identified structural macrostructural elements and shows the structures and structural style that character each part of the Tyennan allochthon. This is an enlarged view of the southern profile CC'. The major elements are assembled based on the associated map pattern. These are the Nye fold map, the mega sheath fold system, and the South Virgin asymmetric fold train. Geographic points are highlighted by the white circles. The structural relationships at the geographic points were used to construct the profile. Differences in younging between the upper Nye fold map and the inverted sequence through the mega sheath folds require a major shear zone along the base of the fold map. Now identifying the major structural elements as components of each structural profile. The fold map knows by the red triangle, the isoclinal fold below the main fold map in the central Tyennan, and by the blue rectangle, the mega sheath fold pair by the bright green rectangle, the asymmetric fold pair wave train by the purple rectangle, the isoclinal fold stack enveloping the mega sheath fold pair by the pink rectangle, the macro fold in the parautochthon by the orange rectangle, and the ophiolite nap by the dark green rectangle. The margin reconstruction diagram is shown as an oblique three-dimensional perspective of the deformed state structural profiles from the southwest coast in the south to Cradle Mountain in the north. The profiles are stacked from south to north and spaced to show the structures and transitions across different parts of the Tyennan region over 200 kilometres length. This slide attempts to show a three-dimensional representation of the structural makeup and geometry of the structures that we have identified as part of this Tyennan synthesis. It is clear that folding dominates at all scales. The diagram also reflects the complexity and spatial variation in structures across the exhumed part of the formerly subducted costal slab. Some of the macrofolds are at high angles to the regional stretch, which is down the dip of the reconstructed margin, whereas others have sheath-like curved hinge lines that are trending towards parallelism with the regional stretching direction. The high-grade metamorphic rocks shown in orange, like the ophiolite sheet, are poorly exposed across the reconstructed margin. They occupy the core of the leading edge fold nap at the top of the presently exposed sheet, that is the Tyennan allochthon. Within the isoclinal fold stack above the megaschist folds of the Davy sheet and as synformal keels within refolded early isoclinal recumbent folds in the Strathgordon area of the Franklin sheet. The deformed upper part of the allochthon is considered to be the Scotch fire metamorphic sheet shown in green and is considered as parautochthon. What does the Tyennan allochthon tell us about continental margin subduction and exhumation? The resultant geometry suggests that emplacement is not just a simple stacking of sheets, that folding is an important part of the exhumation and emplacement process, and folding occurs both internal to the sheets as well as folding of the total composite allochthon, and that the structure of the Tyennan Domain records a complex history. Deformation is partitioned and commonly heterogeneous within and between the sheets. How do these folds develop and what do they represent? This slide is a simple schematic evolution diagram within the subduction channel. The folds form and evolve during buoyant ascent post-peak metamorphism as a competition between tractional forces along the channel boundaries and the buoyancy force within the channel. Geometrically, fold 1 is a schematic representation of the leading edge fold nap. A simple explanation is that at some level within the channel, the tractional force along the upper boundary becomes greater than the buoyancy ascent force, thus effectively pinning the sheet leading edge, and with further buoyant ascent of the trailing part effectively bends the upper part of the allochthon. The result is what we have called a frictional toe stub bending fold. The inset lower left shows how this fold can develop. Note the change in geometry of the layer undergoing simple shear along an upper shear interface. Fold 2 is meant to represent the isoclinal fold stack overlying the megaschist folds, depicted as hinges 3 and 4. Fold 5 depicts the asymmetric fold pair wave train developed at the rear of the sheet or trailing edge, analogous to crumpling developed in a blanket sliding on a table. Thermomechanical modelling of ultra-high pressure rock exhumation by Warren, Beaumont and Jamison in 2008 shows how channelized viscous flow in a subduction zone during buoyant ascent of a subducted margin can produce a large-scale fold nap. This has some similarities to the overall macro geometry of the exhumed Tyennan Cambrian margin. Strain rate variations, the nature of the layering, and changes in material properties of the subducted margin will influence the role of buckling with respect to viscous flow and thereby influence the resultant fold nap geometry and structure internal to the nap. In summary, the Tyennan Domain provides an unparalleled window beneath the now largely eroded and abducted ophiolite sheet. It shows a unique subducted abducted margin crustal architecture and structurally provides insight into the mechanics and processes of continental margin subduction abduction. We hope that this talk has highlighted that 80% of the Tasmanian Wilderness World Heritage Area coincides with the oldest, most deformed and most complexly deformed and metamorphosed rocks in Tasmania, that is the Tyennan geologic region. This region provides perhaps the largest window into the nature, types and extent of crustal structures within rocks subducted and exhumed beneath an overriding slab of oceanic crust, i.e. the abducted ophiolite, and that these rocks preserve aspects of Earth's tectonic processes that have limited global preservation. Thank you.